right, friends, we are on section 3.3. Properties of function. Okay. So remember I said it's kind of a long section? This is a lot. This is all we're supposed to have as a takeaway for this section. We need to be able to identify even and odd functions from a graph, identify even and odd functions from an equation, be able to use a graph to determine where a function is increasing, decreasing, or constant, locate maximums and minimums, using graphs to doing all this with a calculator, and last but not least, find the average rate of change. That's today's. Can we do it? We're gonna try. Da, 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 da. All right, so first we're start. What? First we're gonna identify even and odd functions from a graph. All right, so the definition of an even function, essentially, in words, is that the y-axis evenly divides it into two equal parts. Okay, so like visually, that's what's taking place. Is that the y-axis is dividing it into two even parts. Do we see that? The mathematical definition of what's happening is that the opposite x values have the same y values. So for example, if I'm at x equals 2 and I'm at x equals -2, their values should be the same. So a good way to remember this is y-axis symmetry would be a good way to remember even. Odd functions. An odd function, in terms of words, visually what's happening is it has rotational symmetry around the origin. Okay? Essentially what this means is that if you take this function and you, let me see if I can do it. Pretend that I'm, oh, I didn't trace it all the way. So if you have this function, rotation symmetry around the origin, it means that if you rotate the function and rotate it 180 degrees, that would still look the same. So if I was to take this and where's the rotation button? So this guy, and I was able to rotate it for some reason, I don't know why. It doesn't have rotation feature. But if I could rotate, then it would look exactly the same. Right side up. The other thing, the mathematical way of looking at it is if you see right here, it's not that your opposite x values have the same y value. It's that your x and your y essentially switch places. They're opposites and switch. They're opposites and your x and y values switch. So for example, if I'm here at 1, 2, then this would have to be -2, -1. I think I said that right. All right, so let's look at some theorems. So put it together. A function is even if its graph is symmetric with respect to the y-axis. A function is odd if and only if its graph is symmetric with respect to the origin. about y-axis symmetry and rotational order symmetry.
Okay.
Let's look at some examples. Boom. Is this even a function?
This is not.
So when it says to classify as odd, even, or neither, this is
Because it's not even a function, right?
You see that? Okay. Here we have B. So example B would be
Even was even symmetry with the y-axis. So that would be even.
What about C?
That would be
odd. It goes to the origin, and if I was to rotate this, it would be the same.
You learned it in algebra.
So you want to get out of it. It's cool though. What? All right. Question so far. All right. Now, what about as an equation? How do we identify? Because we can do it visually as graphs, but sometimes this is where we get a little uncomfortable.
So we're identifying as an equation.
There's a couple things that you acknowledge first. Thing number one, we'll take a calculator. You want to pay attention to the power. Remember, it's whether the power is odd or even. That's the first thing you want to pay attention to. Okay.
And then the second thing
you want to pay attention to is how the function is shifted.
And if the function
is shifted left, right, up, and down, then that's how it matters.
what am I thinking?
Hold on, the rest of this example is missing. So that's not the right one.
There we go. It's all out of order.
Oh my gosh.
Okay. Start again. Let me find.
All right. So we're going to talk about these three different functions and how to identify whether they're odd, even, or neither, right? So first one we have is 2x squared plus 3. So we graph the function. Bam. There's the graph of the function. After we would graph the function, we then would decide, is it odd, even, or neither? It is even. And why is it even? There's symmetry. It's symmetrical with the y-axis. Okay. Now, algebraically to prove this, all you have to do is replace x with negative x. Yeah. So you replace x with negative x. And if it comes out to be the original problem, then they are even. So notice here when I replace negative x, I do the math, simplify. Oh my gosh. It comes back to being itself. Oh, so it just goes back to it goes back to being itself. And that's how you would algebraically prove that it is even. Now, if it did not come back to itself, that means that your first conjecture was wrong. Or you did your math wrong. One of the two. All right. Do you think you could prove even algebraically? Sure.
Could you substitute in negative x and be okay?
Yeah. I think so. All right. Proving odd is a little bit more. Okay. So here we have x cubed plus 3. And we are conjecturing that it's odd because its power is what? Power is odd, right? The highest power is odd. So we're assuming that it's going to be odd. So we're going to check it graphically. I check it graphically, and there's a little hiccup. It doesn't rotate through the origin. So it's not. So then therefore, not. So we can conjecture that it's odd, but once we graph it, we can see that it's not odd nor even. because it lacks that rotational origin symmetry, right? This little piece right here, if it went through the
origin, cool. Does it touch here? No. Okay. So to algebraically verify, it's a little more steps. You have to do two things, not just one.
You have to find your substituted negative x, and then also
multiply the entire thing by negative x. So it's gonna be two separate. So when I substitute in negative x, this is what I get. Negative x cubed plus 3.
Okay? That's part 1 of verification. Part 2 of verification is for me to actually multiply g of x by -1. So I have negative times x cubed plus 3. And that gives me negative x cubed minus 3. Part 3 is to check that these are the same. Are they the same?
Are they the same?
Nope. Oh, yeah, here. No, it's the same. Okay, so let's do it again. So for checking odd algebraically, there's 2 steps to it. Step 1 is you have to substitute in negative x for x. Do we see that? And then you get a new equation. Step 2 is you now are going to multiply the function by -1. So you're multiplying the entire function by -1. And all that does is change the signs, right? If I multiply by a negative, it just changes the sign. Or dividing by negative, it changes the sign. And this
It would be a not, because then you compare
part 1 and part 2. Are they equal? Are they the same? No, they're not the same. So my conjecture that it was odd was wrong. The graph proved me also that it was not odd. So this would be algebraic. These would be the same. And it would go through the origin. All right, so let's look at it. Again, so algebraically, what did I do? I also did negative g of x. And I did g of x, and I compared them, and they were not the same because these two are not equal. Okay? Typed out pretty for you. But as you can see, these two things aren't equal. In order for them to algebraically be true, they must be equal. Let's look at one when it is equal. So here we have x cubed plus 4x. And again, we're going to graph it to just make sure we're on the right track. So you can see why it turns out to be odd. So clearly, looking at the graph, this is odd, right? But we see that this is odd. Goes through the origin, and if I rotate this around 180 degrees, it's going to be the same, right, Brandon? Okay. Now we're going to do it algebraically. So algebraically, what should happen is that h of negative x should equal negative h of x. Which means that when I change the x's to a negative, I should get the same result by changing the entire equation to a negative. So if this is true, that it's odd. Algebraically, when I change my x to a negative, and then I change my entire equation negative, they should equal each other. Okay? So when I do h negative x, that means wherever x is now is a negative 4 negative x. And I do negative h of x, which means I'm multiplying the entire thing by -1. They should come out to be the same. So this one comes out to be negative x cubed, and this one comes out to be minus 4x. This one comes out to be, I distribute my negative, comes out to be negative x cubed, and this comes out to be minus 4x. Are they the same? Yes. So am I right that this is an odd function? Yes. That's how you algebraically verify that it's odd. Okay, unit 2 test has 2
Part.
On your unit 2 test, you will have a calculator and a non-calculator because you have to be able to analyze functions, not using a calculator. Oh, so one part will have one part is calculator, one part is non-calculator. For unit 2. So that's why I'm showing you what it looks like graphically and what you would do algebraically. See that? Yeah? Okay. Anyone can tell me if it works as a graph.
Right. It's all typed out.
Thing. Pretty. All right, so now we're on to determining where a function is increasing, decreasing, or constant. Okay? So if a function is increasing, that means from left to right, the values are going up in some form or fashion. If the function is decreasing from left to right, the values are going down. And the function is constant, no changes taking place. Agree? Sound right? Cool. So what that means in terms of a formal definition, instead of saying from left to right, we would read it as a function f is increasing on an interval if interval I, if for any choice of x1 and x2 in interval I with x1 less than x2, then f of x1 is less than f of x2. That is your full formal definition. And literally is saying, as you read from left to right, the values are increasing. That's what that means. Very fun terms. Okay? Unless you plan on taking math analysis or really mainly a math analysis type class, the formal definition shouldn't really be your concern. As long as you understand everything else. Left to right, what's happening? Okay? Just like you read a book, you read the function from left to right. Right? So looking here, from left to right, this function is increasing. It doesn't matter how fast or slow it's increasing. It's just saying, are all the numbers getting larger from left to right? And they are. What your definition was saying is that, and when I look at x1 and I look at x2, f of x2 has to be greater than f of x1. And that makes sense because left to right, we should get bigger. So this would be our increase. Okay.
There's an S.
And then here from left to right, what is it doing? Decreasing. That means that the y values for x1 are going to be greater than x2. And then lastly, our constant. The constant is no changes taking place. The value of x1 equals the value of x2. Yes. Which one? Not enough information for us to conclude. What do you mean? It's constant. Yes. But there's intervals. We're talking about intervals of being constant. A constant function is an even function. But just in general, constant pieces can be, the entire graph isn't going to always be constant or increasing or decreasing.
That's what we're going to explain.
The intervals. Okay.
So as you see here,
We have, what'd you say?
I'm saying right here, we're not
describing whether this is odd or even, because we're just looking at pieces of the graph. So you
don't know what else is happening on that graph. So
there's not enough information to conclude whether this is constant. If
this constant is odd or even.
Like, so for example, this, it could have just been this piece zoomed in, and then the rest of the graph is doing something else. Like when I said there wasn't enough information, there isn't enough information
For us to decide. Now the constant here,
function,
that's an even function. When we're talking about in terms of all of our even functions, yes, that's an even function.
but a constant piece of a graph isn't automatically even. Okay. All right, so determining when something is increasing and decreasing, we talked about it in terms of intervals. Okay.
And remember, there's two ways of writing intervals, either with inequalities or with your brackets and parentheses, correct? Okay, so if this is asking me at what point, at what values of x is the
function increasing? So when I'm reading from left to right, I like to, well, when I was a student, I would go through and put my C's, my I's, and my D's. At what point am I constant, increasing, decreasing? So as I read from left to right, this is a C, this is an I, this is a D, this is an I. Does that make sense? So then when I come to writing my interval, I'm looking, okay, for when do I get I's? Well, I get I's from -2 till 0. So from -2 to 0, I know I'm increasing. I also got an I
from 3 to 4.
You don't have to write the units. You're just listing out where they are. Okay. If I was writing this in terms of inequalities, I would have -2 to 0, and I would have 3
to 4.
Can we do inequalities instead, or
it depends on what it asks.
these are values?
All right, but you need to be comfortable with both of them. Okay, notice when we're describing increasing and decreasing and constant, we are always using parentheses on our intervals, because brackets represent being equal to, and we're not describing where and when you're equal to something, right? All right, so my decreasing interval, my decreasing is from 0 to 3. So x values between 0 and 3. And my constant was from -4 to -2. Be careful and make sure that you're only describing it based on your x's, your x values. How do you feel about reading a graph and telling me where it's increasing, decreasing, and constant? Yeah, good? Doable?
It's kind of like reading a graph with more stuff.
Exactly. You're reading and interpreting. All right. All right. So now we're going to go on to local maximum and local minimum. All right. A local maximum is when you're saying that your graph increases, then it decreases. So we're going to increase and then we decrease. That makes a local max. I, then I decrease. Okay. A local minimum is saying that you are decreasing and then you are increasing, and that makes it a local minimum. Okay, when you're answering this question, when it's asking where it's at, where at means you're giving the x value, what it is means you're giving the y value. I'm asking you, where is your local maximum? You would tell me at x equals blah, 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 blah. If I say, what is your local maximum? You would tell me y equals blah, 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 blah. Okay, where is your x? What is the y? So the way I think about this is x marks the spot. And what is x marking? Your y. Okay. Question. Okay, here's your formal math analysis definition of a maximum and minimum. A little more detailed than what I just told you. But it's basically saying on an interval, what point does it increase and decrease? All that fun stuff. But you can read through that. All right. So here it says at what numbers x, remember what, if any, does f have a local maximum? List the local maximum values. Okay. So where has an actual maximum. Maximum. Oh, I'm on the right track. So maximums, where art thou? X equal what? So I'm looking for, so the best thing to do is go through and identify your increases and your decreases. So we decrease, then we increase, then we decrease, then we increase. Okay? For a maximum, that means you increase, then you decrease. So where is my maximum located? At x equals 0. And what is the maximum value? Y equals 3. Max value. Y equals 3. Where? At x equals 0. Value, y equals 3. Okay, notice that these are called local. We didn't ask for absolute, because if we asked for absolute, would we have it? Because the graph goes on. All right, how do you feel? Okay, now we're gonna do it again, but this time for our minimums. So we had decrease, increase, decrease. And so we're looking for where at x equals what do we have minimums? -2, 1. At x equals -2, and at x equals 1, we decrease, then increase, we decrease, then we increase. Okay? Then it says what, list the local minimum values. What are our local minimum values? Our lowest values are y equals -1 and y equals
0.
If you wanted to, you can list it out as a set.
Pretend that's the world's best race you've ever seen. So -2, 1. And
Y is -1. That's a good
This is gonna get for you.
Okay. Now, if I didn't have a point where it decreases and increase, then I would write NA, not applicable, or no solution, right? But I do have that point, so therefore you write that. All right, so just to make sure that you understand and you're comfortable, I'd like for you to look at this graph and you're gonna list out just the points of where it's increasing and where it's decreasing. So on what intervals am I increasing and what intervals am I decreasing? All right,
Intervals of increasing.
what are thou?
-4.
Increasing?
Oh, increasing. Oh, -2 to 0.
-2 to 0 and there's 1 to infinity. 1 to infinity. I just asked you for your intervals
Intervals.
of
Increasing and decreasing.
I didn't ask for local maximum. Where did this? On what intervals am I decreasing? Negative infinity, -2. And where else am I decreasing?
0. All right. Do we see why we have the infinities in play?
All right, cool. Any questions? Cool. We'll keep it pushing. All right, now we're gonna talk about absolute max and min. Okay? Absolute means out of this entire function, from where it starts with the domain to where it ends the domain, what are your points where this takes place? Okay? That's what we're looking at, the absolute. So for example, if I have this function, the first thing I identify is the domain of the function before you identify the absolute max and min. This function goes from A to B, right? And I'm looking on here for from A to B, what is taking place. So from A to B, I have this increasing, this decreasing, this increasing. But my absolute maximum, the absolute point where I increase and decrease is here. my absolute minimum from where I decrease, then increase is here. Okay, those are my absolute locations. There's no other point on this domain will that happen. Okay? And it's no other point because it's a closed domain. It doesn't go on forever. It has closure. Okay? If you took Cal or take calculus, you may hear them called absolute extrema. And when you hear the word extrema, that's what you're referring to as your maximum and your minimum. You won't deal with that until pre-cal. Calculus.
Not pre-cal.
For the graph of each function, find the absolute maximum and the absolute minimum if they exist. So here, looking at this graph, do I have any absolutes? I do. Right? So I am, this is a decrease, this is an increase, this is a decrease.
Oh.
So my absolute max would be at what?
X equals
3. My absolute min would be at what? At x equals what? 1. Now, what changes here is your absolute, the values may not be the same. So notice that your absolute minimum value is not going to be the same as your absolute, where your absolute min is located. Because what is your absolute minimum value? Your minimum is here. I decrease and I increase.
Oh, yeah.
the X value, right?
Okay, but notice here that if I was to talk about value, like the Y, this would be my minimum value, right? It's not an absolute max and min as far as location based on the definition of absolute max and min, but this would be my minimum value and this would be my max value. Okay, so be careful when reading the question of what they are asking. All right.
Questions? Keep it pushing.
All right, so this is just your definition. If a
Function f is continuous on a closed interval a to b, then
f has an absolute maximum and an absolute minimum, okay? If it's closed, there is a max and a min. Okay? Next is using the calculator to get through this.
where do I make it?
So when the graph is given, the function is given to you, your job is to use the calculator to find it. In the calculator, to find your max and min, you are using second trace. And then once you get the second trace, that's where you have to decide whether you're looking for the minimum or the maximum. And then from there, calculate over the rest. And last is average rate of change. And average rate of change is just a fancy way of saying slope. Can you find the slope? Okay. Monday, if you also like it, we'll go back through and
We start 3, 4.
that's it. We barely made it.
Told you.